Let's get started. Today I'm going to continue with the lecture on probability. We'll actually finish up today and start with queuing theory on Tuesday. Okay, so the topics today are sort of a grab bag of things. I'll finish with the last of the continuous distributions, the power law distribution, and then state some theorems. They're not going to prove it, of course. But these are kind of a useful collection of theorems, something you should know, and we'll end up using some of these as we study statistics, so it's just useful to state them right here. And then the bulk of the lecture, maybe, well, about half, a little bit more than half, will be on really what is meant by joint probability distribution. And this concept of joint probability is something that many students find confusing, and so I'll try to explain it through a very, very simple example, and we'll sort of slowly make it more and more complicated. And at the end, hopefully you have a good understanding of what a joint probability distribution means, or what a marginal means, and conditional joint probability, and so on. And that will allow us to motivate a technique for computing joint probability distributions, or I should say metrics related to joint probability distributions using Bayesian networks. So we can view Bayesian networks as a compact representation of joint probability distribution. So we'll spend quite a bit of Bayesian networks, and Bayesian networks shows up a lot when you're doing any kind of reasoning, AI systems, machine learning. They all use Bayesian networks, and you may run across them elsewhere, but I think it's viewed properly as being a subset of the joint probability distribution, which I have misspelled. Okay, so let's start at the top with the power law. So we saw in the last lecture some laws that show up when, for example, the Gaussian shows up, or the normal shows up, and you have some expectation and you have some variation, a little bit of variation around it, and you model that as a Gaussian, as a normal distribution. Another kind of pattern that shows up quite often is that we have some ensemble or some set of objects. Let's just call them object, let's call it A1, A2, etc. Let's say we have AN, and N is large. Okay, and moreover, what we find is that some objects are more preferred than others. Some objects get in terms of accesses, are accessed more than others, are referred to more than others, whatever, right? And so we have an ordering, and we assume, for example, that you impose the ordering over here, and we'll say that A1 in some sense is A2, and this notation here just means it's preferred to, etc. Okay, and what we can then do is we can think of, for example, the histogram of the number of accesses. So let me make it a bit more concrete. Let's say that you have a library with 1,000 books or 1,000,000 books in it. Okay, the Davis Center library. Now, you can imagine that some books have not been checked out since 1954 or 1957, whenever they set it up. Nobody ever checked it out. Why? Because it's a book that nobody really wants to read. It's a read once, or say write once book. It was written once and nobody read it, so nobody checked it out. So it has essentially 0 accesses, and so it will show up as AN. Basic number of accesses for this is 0. And in fact, one could expect that the number of items with very few accesses, 0, 1, or 2 in the last 50 years, is actually quite large. One can actually expect that maybe 99% of the books in the library, if you have 1,000,000 books, chances are pretty good that of the 1,000,000, only about 10,000 have been checked out more than twice in 50 years. Okay, that's probably true. All right, the textbooks have been checked out, and maybe a few others, and the rest have never been checked out. So what we expect to find is that if you were to draw the histogram, we would have at 0 a lot of books would have 0. Here I'm ranking. Oh, here is the index, and on the y-axis I have the number of accesses to that. Okay, and so there's lots of 0, and then turning your attention to the other side, some books are going to be checked out a lot. Let's say a course textbook for algorithms. Every term, everybody's going to rush and get that. So there's going to be a lot of accesses to some things over here. This one, probably the next most accessed one, is also pretty up. But you know what? It drops off pretty fast. And we get a few in the middle, and then we get nothing else. Okay? So we have this behavior where the accesses to certain things are way more. In fact, if you were to look at the total number of books checked out, almost all the total number of books checked out would actually belong to the first few of these. Okay, so similar situation holds. For example, if you're at Amazon and you're looking at books sold, okay, the books that are ranked the most popular ones, the 100,000 most popular books, probably account for most of the accesses. And then there is this tail of books that are sold ones and twos and so on and so forth. Okay, another similar situation shows up in if you look at the inter-arrival times of packets to a router. When they say the inter-arrival times follow power law distribution, that means that you have lots of packets that are close together. So if you were to look at the inter-arrival times that were to, let's say the inter-arrival time, this is 1 second, and then we have inter-arrival time of 2 seconds and so on, using some quantum, one could postulate that if you have a burst and you're getting packets essentially back to back with zero gaps between them, that becomes very popular, right? Because you have bursts of packets coming back to back, whereas other times are going to be less popular. So this inter-arrival time thing I'm sort of making up, but these other things are certainly observed. So in these kinds of situations, we see what's called the power law. Okay, now I should mention that there are actually two related rules. One is called Zipf's law, or the Zipf distribution. Okay, and that's discrete. And that's exactly what I've been showing over here, is the discrete distribution where the domain, okay, is essentially the set over here, where it's the objects in the ensemble, and we're looking at the number of accesses to it. And we can view the axis divided by essentially AI divided by sigma AI as being essentially the probability. Okay, we defined the probability of the ith book being checked out as being sigma AI or sigma AI. That is your frequentist approach to probability, and we can view that as being a discrete probability distribution over the entities A1 to AN. And so we can say over here that we have discrete probability distribution, and roughly speaking, basically P, the probability that the random variable takes the value AI is essentially something that looks like this, is a to the minus I, where you have some parameters. So we have I'm sorry, what am I doing here? I to the minus a, I to the minus alpha, which just to use alpha as a thing. Okay, so essentially what you're saying that the ith value over here, which is something over here, goes down roughly like this. Okay, so to take an example, if the you have I is 20, then the probability of the 20th thing we access is 1 over 400 if alpha is 2. So if I is 20, alpha is 2, then the 20th item is going to be accessed 1 over 400 times, the 30th item 1 over 900 times, and so on. So it decays fairly fast. So this is Zipf's law, and the continuous approximation to this is called the power law. Okay, so when we take the number of items going to infinity, then we can write down the general form of this is that fx, so the power law, fx equals, there's a parameter alpha minus 1 over x min, which is the smallest value that you can take in the domain, x over x min to the power minus alpha. So the x min parameter essentially allows you to do certain amount of normalization if you need to, which says that's the smallest value x can take, and we have to make sure that alpha is greater than 1, because obviously you can't have a negative there, so alpha is greater than 1. And this is the density function. Now I'm leaving out a normalization term. In fact, we see that if alpha is less than 2, okay, then the expectation of x, which is defined in this fashion, is actually infinite. All right. So what this means is that you're going to have it's basically undefined, and you're going to have this increasingly large values. So for all practical purposes, though alpha less than 2 is okay in this formula, in practice, if alpha has to be greater than 2, okay, we want it to decay fairly fast, otherwise there's too much mass in this thing. I'm going to say one more thing, and maybe that will help you understand this. Essentially what we can do is something like this. We can think of log of f of x, okay, is nothing more than, it's basically given at approximately alpha log of x. Okay, so what does this mean? Okay, if I view this as, in the continuous sense, as p of x or f of x, then on a log-log scale, so if I have on this scale log x and I have here log f of x, I expect to see essentially a straight line. And what is the curve? The curve is, the slope is minus alpha. Okay, so I should probably put over here minus alpha log of x. Okay, so what we're saying over here is something fairly strong. What this says is that let's take the ensemble, let's look at the number of axes, and we will plot it in a sorted fashion, okay, which means the most axis one is called number 1 and number 2, and let's take the limit as n tends to infinity, and what we're going to get over here is, if we plot log x versus log f of x, this is a straight line. In a discrete case, of course, what we expect to see are points that look like this, okay, and in fact, that's exactly what we get. If we were to take the number of accesses to the most checked out book and call that 1, the second checked out book call it 2, etc., and you have to plot the log of the book ID versus the the frequently superposed, the ratio of the number of accesses to total number of accesses. In other words, this value over here, where I put it, this value over here, then it turns out that in fact it is a straight line exactly like this, okay, and the slope tells you what the value of alpha is. So that is a empirical observation which we're trying to capture using the power law. Okay, so in the same way the normal is trying to capture the variations in expected mean, here we're saying that it's not like a book is normally checked out 3 times, over 3 times a year, and some are at 2.9, some are at 2.6, etc., etc., and there's a little bit of variation around 3. No, it's not like that at all. It's the opposite. Some books are checked out 3, some books are checked out 3,000, okay, and some books are checked out 0, and that's what's going on over here. Okay, so that's why you're getting this shape as opposed to a normal where you have a little bit of variation. There's a tremendous amount of variation over here, and in fact, as you can, if you compute the variance of this is alpha between 1 and 2, it's infinite as well, as far as I remember. Yes?
I think the example which we took over here, they might seem reasonable even if we take the exponential decay distribution.
Okay, yes, I'm coming to that. Yes, exponential versus power law, I'll come to in just a minute. I just want to get the concept of this first. Okay, any questions about this over here so far? Okay, so I'll quickly summarize. What I'm saying over here is that we have a set, or in the continuous case, we have a range. Now, it gets a bit tricky when you say, well, how do you do the ordering on the range? Because the range is a continuous range. So we have to assume that, that the range is such that there is a natural inherent ordering. For example, interarrival times, there may be a natural inherent ordering in that continuous range. Obviously, for number of books, is a discrete range. And then we have distribution, where we take this definition of probability, and we can define that the probability that it takes the ith value is essentially the ith value raised to some constant negative power called alpha. And in the continuous case, other than the x-min, it's basically similar, and I left out the normalizing factor, and the characteristic signature is this. Okay, so this is what I've said so far. Now, the question that Aniket asks is this: we've already seen a function which looks like this, which is the sort of the exponential. In exponential case, it kind of looks like this, right? And what's going on over here? Basically, if y equals e to the minus x, then log y. Okay, I should probably show fx just to be. Fx is e to the minus x, then log of f of x is equal to, well, it's just minus x, right? So what happens over here is that here we have a ratio of log of x versus minus x, and maybe an easy way to describe it is that in the power law has way more mass towards the right hand side than exponential for the same value. Okay, so I'm sorry?
They call it fat tail.
The fat tail, heavy tail. So I'm going to come to that in just a second. If you were to zoom in to the distribution, what will happen is that on a linear scale, they both sort of look like this. Okay, you kind of go down like that, and if you plot power law and exponential, they both look like that. But what happens is that if you plot those out, you'll find that essentially the power law looks like this, okay, and the exponential is going to look like minus, on a log scale, it look like minus x, and how am I going to draw this? So this is going to be minus alpha versus minus x. Okay, so the slope of this is minus alpha log x. So the thing is, drawing x on a log scale is a bit crazy, right? It's going to be essentially going exponentially down, okay, because this value here this is on the x-axis is log of x, and this is over here is sort of x. If I'm getting this correct, or minus x, I guess you have to take the appropriate thing down. I have tried figuring this out, and I can't really understand how to draw this properly, but I'll tell you what. If you look at the homework question, I don't know which one it is, I have a table there where I ask you to compare the value of the power law versus exponential for certain values of x, okay? And you'll find that the order of magnitude gap between what the power law says and what exponential says is, like 10 to the 44 orders of magnitude difference for n equals 50, for example. So if alpha is 2, the exponential is way, way, way smaller than the power law, and that's why we call it fat tail or heavy tail. So even though the power law is going down fast, the exponential is going down much faster, okay? So for n equals 50, for example, the exponential has, like 10 to the minus 50 roughly, or something like that. I don't remember the exact numbers, but power law still has something that is non-zero, and this is actually why they call it the long tail or the fat tail. And there is this book that came out about a couple of years back saying that because it's a power law and not exponential, what's going on is that there is some non-zero mass towards the tail. And so if somebody is going to have something that caters to quote-unquote the long tail, from a business perspective, they can make a lot of money. So and the story here is something like this. Let's say that the distribution of books was in fact exponential and not power law. The distribution of sales of books was exponential and not power law. That means that this bookstore, which is the size of this room, would actually carry like 99.999% of all the books that everybody ever want. Okay, there's no point in having a larger bookstore because the amount of money you can make on selling this is not enough. However, if the distribution is power law, what that means is that there's enough mass in the tail that I need a very large bookstore. And I can't build a very large bookstore because, it takes much space for that. I have to have it heated, and I've got to have whatever. It's expensive. It's real estate. However, what Amazon does is to say, look, the bookstore is in the sky. You have this virtual bookstore, and all the books are actually sitting, in some warehouse. In fact, Amazon will actually print a book for you if you want to, right? If you say, I want to buy so-and-so book, it's not there. They tell the publisher, hey, just print it. And you have these mini printers now. You can actually print these on demand. So the bookstore essentially is infinite, which means you can capture all the mass in the long tail. I mean, if you can capture all the mass in the long tail, no small bookstore can compete with you. So the argument is that very, very large internet-enabled e-commerce things like iTunes and Amazon are able to capture on the non-zero probability mass, or I should say non-insignificant probability mass in the tail of the distribution. That's what they call the long tail. So this is another reason of what's going on over here. Okay, applied to the packet arrival process. Okay, the packet inter-arrival times in packets are supposed to be, if the packet arrivals are described by Poisson, as I mentioned, and we'll study more in queuing theory, the inter-arrival process is exponential. Again, we'll see that later in about a week from today, or maybe 2 weeks from today. And the inter-arrival processes are actually shown to be power law. So what that means is that with exponential, the probability of a very long inter-arrival time is practically zero. Okay, it's going to be very, very, very small. With power law, there's a non-zero probability that actually you're going to see larger inter-arrival times. Okay, so it works both ways. Okay, so I think that who was asking what? So that's a power law versus exponential. Now in the notes, all I have is one line saying that power law is greater than exponential, but and I think the numerical will really help you understand how much of a gap there is. But there's a considerable body of business literature on this, which of course I'm not going to go into over here. Okay. Any other questions about this over here? So the other example I have in the book is for website visits, and I guess you can take a look. This is I copied these two figures from a paper called Zipf, Power Laws and Pareto, and what they're showing over here is, if you have it in front of you, is on the x-axis, on the left-hand side is this graph over here, which is it looks kind of drops off very fast. And if you look at the log scale, however, it's a discrete thing because you look at number of visitors to websites. So you say, okay, how many visitors go to google.com, how many visitors go to whatever chapters.ca, and you have that number of accesses to a website. And sure enough, empirically, you see that it looks pretty much like a straight line, and that is your power law in the discrete case. Okay. Any questions about this? All right, I'm going to sort of change gears now. So that was the last of the continuous. I kind of snuck in the discrete as well over here, and we'll start talking about these different bounds and theorems that are useful to have. So these theorems or bounds are useful when you have some kind of you want to get some sense of what is the tail probability. So let me start with the first one. This is called the Markov Inequality. And the Markov Inequality, what you're given is a random variable. Let's just call a random variable which we call x, and we are told that the expected value of x is mu, and that's all you know about it. The expected value of x is mu. That's it. It could be any distribution whatsoever. Any distribution whatsoever. We don't know what the distribution is. All we know is that the probability mass under the distribution curve is 1, and that's basically all you know about it. So what you want to do is we can think of the distribution like this. So here we have the value x, and you have the value fx, and it could be anything. Okay, it could be over an infinite domain, or it could be a non-infinite domain. It could go all over the place, right? As long as the area is under 1. Area under the curve is 1. So we want to say that here is some value a, some constant a, and I want to know what is the probability that x is greater than or equal to a. Okay, and so it's at first glance it looks crazy. How can I know? I mean, the distribution could be whatsoever, anything whatsoever, but it turns out that if we know that the mean is mu, that kind of constrains us. Okay, intuitively what's going on is that the mean, which is say some value over here, okay, if there's a lot of mass on the right hand side, then the mu is going to move to the right hand side as well. Okay, by having the mean be at some particular point for some value of x, you can't really have too much more very far away from the mean. In fact, we can show that probability that x is greater than or equal to a, this is the right hand side, is less than or equal to just mu over a. Okay, and so what we're saying is that as we move to the right hand side, the probability that x is larger than that value keeps decreasing. In fact, it decreases essentially linearly with a. Okay, so as you make something further and further away, this is what you're going to get. Okay, and I guess you have to have, I wonder if you have to have a greater than mu. I don't know. I should look that up. In my notes, I always assumed that a was greater than mu, but I have to check. Okay, I'll just check that. But that gives you kind of a rough and ready bound. Again, in the homework assignment, what you'll find is I've asked you to compute the Markov bound on some value compared to the, I guess it's either the Gaussian or the binomial, I can't remember which one. And you'll see that this bound is very, very, very loose. It can be like 10, 20 orders of magnitude loose. But it's better than nothing. Okay, so if you want just like a rough and ready bound, that's what you have. And of course, if you know something better, then you can plug it in. But it's really remarkably simple, and so it's a useful tool to have. Yes.
If a is smaller than mu, then it's trivial. The probability is smaller than 1.
If a is smaller than mu, yeah, but.
And I think it's random variable must be positive.
So random variable has to be positive. Yeah, it has to be positive, yes. Absolutely. So it is zero bounded. So I should probably state that. Random variable x is greater than, I guess, I don't know if it's equal to or greater than, but yeah, and a is greater than 0 as well. I should probably state that as well. Otherwise, that doesn't work. So, but I don't know about, so if a is smaller than mu, yeah, it's not very helpful to you to say that it's less than 1. Yeah, so it's a trivial bound when it's less than when a is less than mu. Okay, anything else? Okay, so we'll go to something that's slightly more useful, or well, this is useful too, but this is called Chebyshev's inequality. Now, it turns out that you can spell Chebyshev in about 100 different ways, with random assortments of C's and H's and T's. And I can't remember. Okay, I have CHEV here, and I think I put C. I don't know. I may have used S somewhere else. There was a joke I heard that in the Yale Computer Science department, this is probably in the mid-80s, the root password was Chebyshev, and you could tell somebody it's Chebyshev, and they wouldn't know what the password was. Okay, because there's so many variations of the word Chebyshev. I picked one out of a hat, and I think I used 2 different ones because I have it one way in page 22 and different way in page 23. Anyway, so here we have, and let me be careful, so x is a random variable. Again, we don't know much about it. We do know it has a finite mean. I should probably say over there it's a finite mean as well. It's a finite mean mu, and it has a variance sigma squared. And for any constant a, now we don't have to say that a is positive. For any a, we can say the probability that x minus mu is greater than or equal to a is less than or equal to sigma square by a square. And so let's just sort of unpack this. So what's x minus mu mod? Well, again, we have over here some distribution. Again, it can be positive or negative in this case. And we're saying that it has some mean. Let's say this is the mean mu. And what we're doing is that we have some value a, and so this is a over here, and this is a over there as well. So we're saying that the distance of x from mu is greater than a. So that means this area here, the 2 tails, the left tail and the right tail, the sum of the masses in these 2 tails is bounded by this value sigma square by a square. Okay, and that's basically what we are saying. Now, what happens if a is negative? I guess it doesn't really make any sense. It doesn't really help you for a if a is negative or not. So again, typically a is positive, but again, I should probably check is a positive. I think. Okay, I'll just double check on that. But my notes say it's for any a. So typically, again, I use it for positive a. What we're saying over here is that I don't know anything about the distribution function. However, I know the mean, and I know its variance, and now I can tell you the total mass on both sides. And if you know it's symmetric, then of course we can get a little bit better. We can get a handle on the left or the right. But if you don't know it's symmetric, that's all you get from the Chebyshev inequality. Okay, and that is basically it. Again, this is useful when we have arbitrary distributions and we want to get some idea of how bad can it be, you know, because these kind of tail probabilities, these areas under the curve, in some sense are usually the badness in the system. Okay, it's some measure of badness in a system. What do we mean by that? Let's say I'm designing a web server, all right? And I want to know what is the probability that the number of hits in any 5-minute period exceeds the capacity of the web server, because then I'll get the server is out of bound kind of thing, or server has too much, is busy. I don't want to give that busy signal. So that if I have some random distribution over the number of hits, okay, and I size it for that particular value, I size it over here, this tail probability is the bound on the amount of badness. So I can say, all right, I've bounded even using, even though I don't know the complete shape of the distribution, I kind of can tell you that this bound, even though I cannot do the mathematical integral on this or even the numerical integral on this, I can approximate it, and I can tell you that with 99.99% confidence, okay, because that's what this bound gives you, the number of visits to my website will not exceed certain value, okay, and so so the badness, which is getting the signal server is overloaded, is bounded. Okay. Similarly, we can bound packet loss probabilities in a buffer. So I have packets coming into a router and packets being served, and I want to size the buffer so that packets don't get lost. Well, again, the number of intensity of packets coming in is a random variable. It has some distribution. What I can do is I can say, okay, if the buffer is this big, the probability that it doesn't exceed it, I can bound using a Chebyshev or Markov bound, and that allows me to say, okay, packet loss probability is bounded. All right, so let me stop here for a second. We'll take a break and we'll come back and talk about these other two things over here. So law of large numbers has two variants, weak law and strong law, and I'm going to tell you about the strong law of large numbers. And people claim, at least people in probability theory claim this is one of the most important theorems in probability. I guess so. I mean, it's not something that that I've run into very often, but it's at the basis of many important theorems and proofs. So, what does it say? Let me be very precise. So, what we're saying over here is that we have some kind of random variable. And I should say, okay, right. So I have a set of random variables. And I'll call them, x1, x2, etc. until xn. Okay. Now what I'm going to do is that they are independent. I'm going to assume they're independent. And assume that they have the same distribution. Okay, so whatever the distribution is, I don't know what it is, but they're the same distribution, and these two are often standardized to IID, where independent identically distributed. So we'll say x1 to xn is a collection of IID random variables. It means you're independent and identically distributed random variables. And we also say that they have the same expected value, which is equal to mu. Okay. Now, let me first state the theorem, and then I'll tell you how to understand, at least one way of understanding it. Limit n tends to infinity, x1 plus x2 plus xn in plus mu equals 1. All right. So the way to understand it, okay, a way to understand it is this. I have some phenomenon going on, and what's going on is that I'm going to sample it. I'm going to measure its value, and each time I measure it, I call it x1, I call it x2, x3, right? So I assume that that phenomenon is such that each of these samples I'm getting are independent. Okay, and since this is the same phenomenon and the phenomenon hasn't changed, it's stable or stationary, they're all identically distributed, and in fact the phenomenon has inherent or intrinsic mean value mu. What this says is that if I take the observations and sum it up and divide by n, the number of observations, I'll in fact find mu as n tends to infinity. I'm guaranteed that the mean of these samples in fact becomes the true mean. Okay, this is the mean of the samples is equal to the true mean with probability 1. Okay, so as long as we are making independent samples, all right, they will approach the true mean with probability 1. So let's take a kind of an example which is relevant. So there are two elections going on. So let's take the Canadian election, and we want to find out the probability that let's say Dion gets 30% of the votes. Okay, so we want to compute that probability, and so what is the, of course, no person is going to vote 30%, right? I mean, you can't say I'm going to vote 30% here, 30% there. So what we're going to do is that we're going to have some sample of, let's say, 100 people. I'm going to call them up, and I'm going to find out what